Hello, everyone. My name is Joshua Zhao, and I'll be presenting the paper Leak and Learn, an attacker's cookbook to train using leaked data from Federated Learning. This work is done in collaboration with Ahan Dabolkar, Atul Sharma, and Professor Saurabh Bagchi. Prior attacks in Federated Learning have shown that user data can be leaked from the updates. But despite impressive results showing that they can break defenses such as secure aggregation or federated averaging, these works have not explored what to do with the data after it has been leaked. That is precisely what this work is looking into. We asked the question, how well can the leaked data be used to train machine learning models? There are three main scenarios which we'll be exploring. One is benign federated learning training in addition to centralized training, which we use as a baseline of comparison. The second is training a model completely from scratch using only the leaked data. And the third is improving the final federated learning model with leaked data. There are two main classes of attacks which we'll be looking into. Gradient inversion is an attack that is done through an optimization process. This attack does not require manipulation of the model parameters or architecture, but is computationally costly to do. Linear layer leakage, on the other hand, does require manipulation of the model parameters and architecture. However, despite this, it is able to break defenses such as secure aggregation, and the images that are leaked are near verbatim copies of the training data itself. Using these two attacks, we iterate over the entire MNIST and CVPR10 datasets. For linear layer leakage, we also look at tiny ImageNet. Gradient inversion takes a long time to compute. For instance, with a batch size of 4 on CVPR10, it would take over 61 days to iterate over the entire dataset using a NVIDIA A100 GPU. We also see that with a larger batch size comes a decrease in the reconstruction quality as the PSNR and SSIM scores decrease. Linear layer leakage, on the other hand, does not leak all the images, and the leakage rate is relative to the fully connected layer size. Now that we have leaked the data, we train models completely from scratch. Linear layer leakage reaches very close to centralized performance on CVPR10 and MNIST, and regardless of the fully connected layer size, still achieve a very competitive performance. However, for tiny ImageNet, when we decrease the fully connected layer size, essentially decreasing the total number of images leaked, the model accuracy drops by over 10%. Gradient inversion, on the other hand, is very competitive to centralized performance for a small batch size on CVPR. But surprisingly, regardless of the batch size on MNIST, it is still worse than federated learning. There are some additional experiments which we run in the paper, and we will cover two of them in this talk. For linear layer leakage, training with a very small percentage of leaked data still yields model performance increase. For instance, with just 5% of leaked data, we get nearly a 10% model performance increase compared to the federated learning model baseline. For gradient inversion, we look at removing some of the worst images that are reconstructed from the training. With a PSNR below 12, these images are nearly irrecognizable. But a surprising thing that we find is that removing these images from training still results in a model performance decrease. And interestingly enough, if we train only on these really bad images, we can still get a test accuracy of about 45%. What this means is that these images still have some useful information to contribute to model training. To finish this talk, we'll give a summary of these methods when training models on leaked data. Gradient inversion is very computationally costly, and larger batch sizes result in lower performance reconstruction quality and ultimately worse model performance. However, this is not interesting by itself. What is interesting is that even the images with very poor reconstruction quality are still able to positively contribute to model training. Prior work would have completely discounted these images as they are irrecognizable, but we find that they are still useful for machine learning. Another interesting thing we see is that the attack performs very poorly on a dataset like MNIST, where regardless of the batch size, it still has worse performance when training models compared to federated learning. And this is despite being able to perform reasonably well on CVPR10. This is a surprising fact, as MNIST is typically considered easier than CVPR10. For linear layer leakage, we see that there's very good reconstruction quality, and ultimately the model performance is quite good. For some datasets such as CVPR10 or MNIST, the percentage of data matters much less than a dataset such as tiny ImageNet. What this means is for these larger datasets, efficiency is still very important, as having a large fully connected layer size adds a reasonably large model size overhead also. Another thing to note is that the linear layer leakage process does not match images with leaked labels. Rather, linear layer leakage itself does not require labels for the process. This is a strength of the attack when leaking images, But interestingly enough, it becomes a weakness when trying to train models on the leaked data. Manually leaking all the leaked data is a very tedious process. As such, this is still an open problem for linear layer leakage. That's all for my talk today. Thank you very much for listening.